Hey everyone, and welcome. Today we're going to talk about one of the most incredible, most important technological shifts in all of human history. We're talking about the jump from these big, clunky glass tubes to the tiny little silicon chips that, well, they power pretty much everything in our modern world. I mean, just look at the difference. On one side, you've got the vacuum tube. It was the absolute workhorse of early electronics. And on the other, you've got this beautiful, intricate silicon crystal lattice. One is huge and works in a vacuum. The other is microscopic and works inside a solid. So the big question is, how in the world did we get from that to this? Well, that's what we're going to unpack today. All right, so before we could have pocket-sized supercomputers, we had to start somewhere. And for electronics, that starting point was the vacuum tube, or what a lot of people called the valve. For decades, this was the fundamental building block. But, it came with some pretty major problems.
So how do these things actually work? The basic idea is actually kind of straightforward. You take a piece of metal, the cathode, and you heat it up until it literally starts boiling electrons off its surface. It's wild. Those electrons then fly through a vacuum to get to another piece of metal, the anode. And to control that flow, there's a little grid in the middle that acts like a gate. But here's the key part. All of this has to happen in a vacuum. Why? Because if those electrons bump into any air molecules, they just lose all their energy and the whole thing stops working.
And this is where the problems really start to pile up. I mean, look at this. Vacuum tubes were huge. They were so bulky, they sucked up a ton of power and needed really high voltages. We're talking like 100 volts just to get going. And because you've got this super hot element burning inside a fragile glass bulb, they had a pretty short lifespan and were just not reliable. This was never going to be the technology that you could shrink down to fit in your pocket. No way. So obviously, we needed a better way. And the idea for the next big thing, the real revolution, started way back in the 1930s. It was this radical new thought, what if you could control the flow of electricity inside a solid material? Without all the heat, without the vacuum, without the glass bulb. And this is that idea in action. Instead of boiling electrons off a hot piece of metal, what if you could just use simple inputs, like a little bit of light or some gentle heat, or even a tiny voltage, to create charges that could move around right there inside the solid block itself? No big heating element, no giant empty space needed. This was an absolute game changer. Let's just stop and think about that for a second, because this is the whole shift right here. We went from trying to control electrons as they flew through empty space to controlling them as they moved through a dense, solid crystal. It's a completely different way of thinking, a completely different physical world. Okay, but this brings up a huge question. What kind of material can even do this, right? It can't be a metal because metals conduct electricity all the time, there's no control. And it can't be an insulator because those hardly conduct at all. We needed something different, something in between. We needed a material that was in the Goldilocks zone. Not too hot, not too cold, but just right. And this chart shows us exactly where to find it. You see, materials are basically classified by their resistivity, which is just a fancy way of saying how much they fight against the flow of electricity. Way over on the left, you have metals. They have super low resistivity, like 10 to the minus 8 ohm meters, so electricity just flows right through. Way over on the right, you have insulators with ridiculously high resistivity. But right there in the middle, that's our Goldilocks zone. That's where you find the semiconductors. They're the perfect middle ground. Okay, so we found our special materials. But to really get why they're so special, we've got to zoom in. I mean, way, way in, down to the atomic level. And we have to talk about some really cool physics. We need to talk about something called the band gap. So think about it like this. A single isolated atom, like you see on the left, has its electrons in these very specific separate energy levels, kind of like planets in very strict orbits. But when you mash billions and billions of these atoms together to make a solid crystal, all those orbits start to interact and merge, and those neat little energy levels, they smear out into these wide continuous energy bands, which you can see forming there on the right. Now, inside this whole structure, there are two bands that are super important. The lower one is called the valence band. That's kind of like home base for the electrons. It's where they normally live, and it's usually totally full. The upper one is the conduction band, and it's usually empty. Think of it like a highway. For a material to conduct electricity, an electron has to get enough energy to jump from its home in the valence band up to the highway of the conduction band, where it can finally move around freely. And at space between home base and the highway, That is the single most important idea in all of this. It's called the forbidden energy gap. It's this zone of energy where electrons just aren't allowed to be. To get to the conduction band, an electron has to make a clean jump, all the way across. And the size of this gap? Well, the size of this gap determines everything. It's what makes material a conductor, an insulator, or our special friend, the semiconductor.
Seriously, it all just comes down to the size of this one tiny gap. So let's look at how this one little property creates the three main types of materials we see everywhere. First up, the easy one, metals. In a metal, the valence band and the conduction band actually overlap. There is no gap. Or, you can think of it as being zero. This means electrons can just slip right into the conduction band with practically no effort at all. And that is why metals are such fantastic conductors.
Now, let's swing to the other extreme, insulators. In this case, the energy gap is a giant chasm. We're talking more than 3 electron volts wide. For an electron to make that jump, it would need a massive jolt of energy, way more than it could ever get from just sitting at room temperature. So the electrons stay stuck down in the valence band and no current flows. Simple as that. And that brings us to the hero of our story, semiconductors. Here, the energy gap is small. It's manageable, less than 3 electron volts. At super cold temperatures, it acts just like an insulator. But, and this is the magic part, at room temperature, there's just enough thermal energy floating around to give a few electrons the little kick they need to hop across that small gap and get into the conduction band. This creates a little bit of conductivity. And the best part? It's controllable. So there you have it, the whole story in one picture. Metals have overlapping bands, which means easy peasy conduction. Insulators have a massive gap that pretty much blocks all conduction. And then there are semiconductors, with that perfect, just right gap that lets us decide whether it should act more like a conductor or more like an insulator. So let's just step back and bring it all together. We've gone from a big, hot, clumsy glass tube all the way down to understanding the quantum physics happening inside a tiny crystal. And that journey from this abstract theory to an incredibly powerful technology is what made the entire digital age possible. Think about the ground we just covered. We saw the evolution from those old vacuum tubes to this incredibly precise atomic-level control. We learned how we can classify materials just by looking at the resistivity. And, most importantly, we dove into the energy band theory and saw how the size of that tiny energy gap is the key that unlocks everything. Look, if you remember one thing from all of this, let it be this. The entire digital revolution, all the ones and zeros that run our world, it all comes down to one simple, unbelievably powerful fact. We can take a semiconductor, and by playing with its energy bands, we can make it switch. We can make it go from being an insulator to a conductor, on and off, on and off. That's the switch. That's the switch that powers everything. We literally built our entire modern world just by figuring out how to control a microscopic, forbidden gap inside a crystal. It really makes you wonder, doesn't it? What other seemingly small, fundamental property of the universe are we going to harness to power the next great leap? Thanks for joining me.